nibbling on sponge cake, watching the sun bake. All of this tube is covered with oil. Strumming my six string.
Reefs are carbonate bodies built up mainly by framework-building benthic organisms such as corals. They're wave-resistant structures that form in shallow waters on carbonate platforms. The term reef is used by mariners to indicate shallow, rocky areas at sea, but in geologic terms, they're exclusively biological features. Reef buildups are sometimes referred to as bioherms. Carbonate buildups that do not form dome-shaped reefs but are instead tabular are known as biostromes. Scleractinian corals are the main reef builders in modern oceans, as they have been for much of the Mesozoic and Cenozoic. These corals are successful because many of the taxa are hermatypic. That is, they have a symbiotic relationship with algae, zooxanthellae, that allows the corals to grow rapidly in relatively nutrient-poor waters. So they basically have enslaved organisms that produce them food. They in turn protect the organisms from being consumed by other organisms. The other main modern reef builders are calcareous algae. The fleshy green segments of Halimeda contain oatmeal flake-sized grains of aragonite. These are made up of gazillions of tiny aragonite needles. Also seen here are neogonolithon and amphiroa, two high magnesian calcites. These all contribute to the fine-grained material that makes up a reef. When Halimeda reproduces and dies, it releases these fragments to the sediment. Reef-forming organisms. The earliest reef builders were cyanobacterial, creating stromatolites. These were followed in the Paleozoic by rugose and tabulate corals, as well as calcareous sponges, including stromatoporoids, that were particularly important during the Devonian. Perhaps the most unusual reef-forming organisms were a type of bivalve known as rudists. The shells of these mollusks were thick and conical, forming massive colonies that are characteristic of many Cretaceous reefs. Not only have the kinds of reef-forming organisms varied through time, but also the relative significance of the reefs as depositional environments has changed, with 4 peaks of dominance in the Phanerozoic separated by times when mud mounds were the more common bioherms. Modern reefs can be divided into a number of distinct sub-environments. The reef crest is the site of growth of the corals that build the most robust structures, encrusting in massive forms capable of withstanding the force of waves in very shallow water. They can take a beating. Descending the reef front, these massive and encrusting forms of coral are replaced by branching and more delicate plate-like forms in the lower energy deeper water. Behind the reef crest is a flat reef, also comprising relatively robust forms, but conditions become quieter close to the back reef area, and globular coral forms are common in this region, such as the brain corals. In addition to the main reef builders that form the framework, other organisms play an important role as well. Encrusting organisms such as bryozoan and calcareous algae help to stabilize the framework, and the remains of a wide variety of organisms that live within the reef provide additional mass to it. Calcareous algae can produce 70 or 80% of the carbonate mass of a reef, for example. There are also many organisms that remove mass from the reef structure, a process of bioerosion carried out by some types of fish and mollusks that bore into the reef.
Hump-head parrotfish, nearly 1.5 meters in length. Their jaws are so powerful they can bite through rock. When they descend to feed, the reef itself is under threat. They are indiscriminate feeders, taking both rock and coral alike in their quest for algae. These fish play a large part in the erosion of the reef. The rock and coral they swallow emerges later as a fine sand. On a single reef, they can produce tons of it every year. This soft sand forms the tropical beaches that we find so alluring. Over time, the sand builds up to form an island, which is then colonized by animals and plants. Trees take root. Birds arrive. The guano from thousands of terns which have chosen to nest here enriches the sandy soil, which then can support more plants.
The voids between the framework structures may be filled with the remains of organisms, debris formed by the mechanical breakdown and bioerosion of the framework, and by carbonate mud. If burial occurs before the voids have been filled with sediment, crystalline calcite cement may subsequently be precipitated during diagenesis. Breakup of reef core material by wave and storm action leads to the formation of a talus slope of reef debris. This four-reef setting is a region of accumulation of carbonate breccia that forms bioclastic rootstones and grainstone facies. As these are gravity deposits formed by material falling down from the reef crest, they build out as steeply sloping depositional units inclined at 10 to 30 degrees from the horizontal. Behind the reef crest, the back reef is sheltered from the highest energy conditions and is the site of deposition of debris removed from the reef core and washed towards the lagoon. A gradation from rootstone to grainstone deposits of broken reef material, shells, and occasionally ooids forms a fringe along the margin of the lagoon. Three main forms of reef have been recognized in modern oceans, first by Charles Darwin in the middle of the 19th century. Fringing reefs are built out directly from the shoreline and lack an extensive back reef lagoon area. Barrier reefs, such as the Great Barrier Reef of eastern Australia, are linear reef forms that parallel the shoreline but lie at a distance of kilometers to tens of kilometers offshore. This provides space for a large area of shallow, low-energy back reef lagoon area, which in itself is an important ecosystem and depositional setting. In open ocean areas, coral atolls develop on localized areas of shallow water, such as seamounts, which are in turn the submerged remains of volcanic islands. In addition to these settings of reef formation, evidence from the stratigraphic record includes that there are many examples of patch reefs, localized buildups in shallow water areas such as epicontinental seas, carbonate platforms, and lagoons. Present-day reefs are predominantly in tropical seas, occurring up to 35 degrees latitude north and south of the equator. This may not have been the case in the past. First, other reef builders live in different environments. In modern seas, coral and algae build reefs at higher latitudes, and the environmental tolerances of extinct taxa aren't clearly known. Second, even if the reefs are made of corals, then it must be remembered that pre-Mesozoic groups, the Rugosa and Tabulata, may not have had symbiotic relationships with algae that is such a distinctive feature of the Mesozoic to present-day scleractinian corals. Their distribution in the seas was more controlled by the availability of nutrients. The growth of coral reefs can normally keep pace with both tectonic subsidence and global sea level rise. The cessation of reef development is therefore usually due to changes in environmental conditions, such as an increase in the flux of terrigenous clastic material or a change in the nutrient supply. When this occurs, the dominant facies is fine-grained pelagic material, similar in character to deep-sea pelagic carbonates. Pelagic carbonate sedimentation is considerably slower than shallow marine accumulation rates, resulting in much thinner layers over a given period of time. Materials deposited under these conditions are called condensed sections, with potentially millions of years of accumulation as a shallow water deposit 2 or 3 orders of magnitude thicker. A carbonate mud mound is a sediment body consisting of structureless or crudely bedded fine crystalline carbonate. Modern examples of carbonate mud mounds are rare, so much less is known about the controls in their formation than is the case for structural reefs. From studies of mounds of fine-grained carbonate in the rock record, it appears that there are 2 or possibly 3 types. Many mounds are made up of the remains of microbes that have calcareous structures, and these microbes grew in place to build up the body of sediment. Others have a large component of detrital material, mostly the remains of algae and bacteria, that have been piled up into a mound of loose debris. It's also possible that some skeletal organisms, such as calcareous sponges and bryozoans, are responsible for building carbonate mud mounds. They appear to form in deeper parts of the shelf than reefs, but within the photic zone. Distal regions of carbonate shelf sedimentation are principally fine-grained deposits. These carbonate mudstones are composed of the calcareous remains of planktonic algae and other fine-grained biogenic carbonate. This facies is found in both modern and ancient outer platform settings, and when lithified, the fine-grained carbonate sediment is called chalk. Similar facies also form in deeper water settings. Chalk deposited in shallow water may contain the shelly remains of benthic and planktonic organisms, and there's extensive evidence of bioturbation in some units. Chert nodules within the beds are common in places, the result of reprecipitation of silicious organisms. Bedding is observed as slight variations in the proportions of clay minerals that occur in most chalk deposits, or by variations in the degree of cementation. Deposits of this type may be found in strata of various ages, particularly from the Mesozoic and Cenozoic, are most commonly found in late Cretaceous in the northern hemisphere in a stratigraphic unit which is called the chalk. A number of different carbonate platform morphologies are recognized, the most common being carbonate ramps that are gently sloping platforms, and rim shelves that are flat-top platforms bordered by a rim formed by a reef or carbonate sand shoal. The tectonic setting influences the characteristics of carbonate platforms, the largest occurring on passive continental margins, while smaller platforms form on localized submarine highs, such as fault blocks in extensional settings, and on salt diapiers. Essentially, the salt bubbles up from below, pushing a topographic high into a basin that is colonized by carbonate producers. The different types of carbonate platform can sometimes occur associated with each other. Isolated platforms may be a carbonate ramp on one side and a rim shelf on the other. One form may evolve into another, with a ramp evolving into a rim shelf as a fringing reef develops. In the case of carbonate ramps, the bathymetric profile of a carbonate ramp and the physical processes within the sea and on the seafloor are very similar to an open shelf with clastic deposition. The term ramp may give the impression of a significant slope, but in fact the slope is a gentle one of less than a degree in most instances, in contrast to slope environments associated with rim shelves, which are much steeper. Modern ramps are located where reefs do not form, such as in regions of cooler waters, increased salinity, or relatively high input of terrigenous clastic material. However, in the past, carbonate ramps were formed in a wide range of climatic and environmental settings, especially during periods when reef development was not widespread. In macro to mesotidal regimes, tidal currents distribute carbonate sediment and strongly influence coastal facies. Wave and storm processes are dominant in microtidal shelves and seas. The effects of tides, waves, and storms are all depth dependent, and ramps can be divided into 3 depth-related zones: inner, mid, and outer ramp. Inner ramps are shallow zone, most affected by wave and or tidal action. Coastal facies along tidally influenced shorelines are characterized by deposition of coarser material in channels and carbonate muds on tidal flats. Wave-dominated shorelines may have a beach ridge that confines a lagoon or a linear strand plane attached to the coastal plane. Ramps with mesotidal regimes will show a mixture of beach barrier, tidal inlet, lagoon, and tidal flat deposition. Agitation of carbonate sediment in shallow nearshore water results in a shore face facies of carbonate sand bodies. Skeletal debris and ooids formed in shallow water form bioclastic and oolitic carbonate sand shoals. Benthic foraminifera are the principal components of some tertiary carbonate ramp successions.